Hi, dear students. This record is about mesh size. Finer mesh size. Of course, to be able to increase the accuracy of the analysis, stress analysis, well, you know, one thing to do is that decrease the size of the finite elements by which have more elements. To be able to find the solution as exact, the elements ought to be in differential size, infinitesimal small size, and then can obtain differential equations. And then when we take the integral, the solution will be exact. But for some geometries, for some type of loading, integration method is quite difficult. In some cases, even cannot find the results. So that's why we have numerical techniques, numerical analysis, finite element analysis, finite volume, finite difference, such methods. Obvious, decrease the size of element by which can obtain the result more accurate. But of course, more finite element requires more powerful computers, hardware, and also memory. It requires greater memory size. An ordinary personal computer cannot be used if we have lots of finite elements, workstations, or some special difficult complex problems even need to use supercomputers. So at this point, a clever solution helps us. If the geometry of the object, structural element, is not changing monotonely, while the shape is the same, size is the same. So, if it is such a part, then we can use greater sized elements. But if there is a abrupt cross-sectional changing from say greater to smaller or vice versa, or within the structural element we have some empty spaces such as a hole, then yes, we know quite well in the vicinity of such parts, mathematically speaking, discontinuities, in the vicinity of discontinuities, we have there will be stress concentrations. Um, yes, we know from the theoretical and some experimental studyings, when a structural member contains a discontinuity, such as a hole or sudden change in cross-section, high localized stress can also occur near the discontinuity. So, since it is so, in the vicinity of discontinuities, to be able to find the results more accurately, at such places we may use smaller sized elements, more elements. Not the entire of the body, but only at such parts, abrupt geometrical changings or discontinuities, empty spaces. In the vicinity of such parts, use smaller sized elements, by which increase the accuracy of the solution. Thanks to this technique, can still continue to use an ordinary computer, not supercomputer. Um, Okay, then study on a famous example, well-known example. Okay, for instance, yeah, we have a prismatic object and it has a hole. Well, hole is a discontinuity, such an empty space. When we select the cross section where we have such an empty space and calculate the engineering stress, of course, at the cross section, calculating the cross sectional area, considering such an empty space, find the stress value average. But when we determine the stress, where especially in the vicinity of the discontinuity, yes, can see that the stress value in the vicinity of such a discontinuity is much greater than the average engineering stress. So in short speaking, we say that over there we have a stress concentration. Okay, for instance, say the average stress is in this order, but just in the vicinity of the empty space, stress will be much higher. It is said stress concentration. In this figure, yes, not empty space, but we have an abrupt geometrical changing. The cross section abruptly changes here from D to the lower one. Okay, the engineering solution to be able to decrease the maximum stress, avoid using sharp edges, sharp corners. We round the edges. Interior edges are to be rounded to be able to prevent weakness, to be able to decrease the stress concentration. Okay. We have a valuable studying in the literature. At that time, since there was no computer, no CAD environment to solve such problems, to study on such analysis, we use photoelastic methods, some special solution techniques. Okay, we have a valuable article, and in the article we have the results of such analysis. Here at this point we define stress concentration factor. K is the commonly used letter, okay, to say stress concentration factor. It is defined as maximum stress within the structural element. We have the maximum value in the vicinity of abrupt changing or if exists the empty space divided by the average stress value. Okay, considering the geometry of the body at the cross section, can easily calculate the average stress. And then if we know the K factor, multiplying K factor with the average stress, then can find the maximum value of the stress concentration factor. Okay, in the output of the valuable academic studyings, yes, we have for this case such a loading, such a graph. Here it has been verified that K factors not depend on the material. Completely depend on the geometry. Here, if it is a slab with a hole, then the geometric factor, it is the parameter to use to determine the K factor is diameter of the drill divided by the dominant size of the prismatic body. But in this figure, the diameter of the drill is lowercase d. It is reduced, has been denoted with letter r, and the height of the prism, if we say that it is the front view, then the capital D has been used to say the height of the prism. That ratio is the parameter. Well, if we know the geometry, size of the slab, and it is drilled, then can find this ratio. And then from the graph, for instance, ratio is, let's say, 0.45. Okay, reach to this point corresponds to that K factor, 2.2. And then multiply the K factor with the maximum stress, say, average stress, and then find the maximum stress value. That is the expression. If there is a fillet between the smaller sized part and the other one, then yeah, from this graph, it is the graph to find the K factor, stress concentration factor. Can directly see that, well, if the filleting radius is 0, this means the interior edge is a sharp edge. Then from this graph can see that K factor goes to infinitely large value. So well, that's why we say sharp interior edge cause to weakness. Thank God in practice, radius cannot be 0. But if it were 0, then stress value will tend to go to infinity. Okay, increasing the rounding radius, filleting radius, while following this curve, can see that, well, decrease the maximum stress. Maximum stress is decreased because we have used a smaller K factor with the increasing rounding radius. The other effective parameter is well, the ratio between the cross sections, the size of the greater cross section. It precedes the fillet, divided by the size of the smaller portion. It follows the rivet. Between the smaller size part and the larger one, we have rounded edge, fillet. Rounded interior edge is called fillet. Okay, well, beforehand we used this graphs, but today, well, in CAD environment, well, can determine the stress values using the tools of software. Here, since the risky part is at the place where we have a discontinuity or abrupt geometrical changing, to be able to, we need to determine the stress value more accurately in the vicinity of such risky places. Okay, then, but the other part of the object, yeah, well, no discontinuity, the geometry is monotonely the same, and also the size is not changing. So if it is such a part, then to be able to decrease the computation time, to be able to have an ordinary computer eligible to use for solving such a problem or deal with such an analysis, yes, well, in the vicinity of abrupt changings and or and the discontinuities, empty spaces, use a smaller sized finite elements. In other words, use finer mesh, smaller size mesh. The other parts where the geometry is monotonely the same in shape, in size, use greater size elements. If we use this technique, then continue to use an ordinary computer. Okay, um, related with such things, such cases, then yes, correspondingly in the structure of software can find finer mesh facilities to use finer mesh, small size elements. In the structure of inventor, well, can use two different techniques. Uh, one facility, in one technique, we use local mesh control facility. In the other technique, we use refinement technique, refinement facility, mesh refinement facility. In this record, I'm going to talk about both of them. Okay. Well, in doing this, I'm going to use, well, which example? Similar object in shape. Sorry, well, this is the wrong presentation, I think. No, not this one. Yeah, okay. That is the technical drawing. Well, it is a slab. Well, from the technical note, I see that its thickness is 6 millimeters. Width is 150. The height of the prism is 50. Okay, then I'm going to first create the solid model of the object. You see it has a simple drill. The location coordinates 75, 25, diameter 19. Well, the center point of the drill in this example is at the centroid of the surface. Okay, then create the model of this one. I'm going to define the work as a project obeying to the recommendation. In the memory of the computer, first I'm going to create a special folder. Say that the name of the folder, since the record is about finer mesh, mesh control, small size mesh, refinement technique, say that mesh control. For that purpose, I'm going to name the project folder using such a phrase, mesh control, or just I said mesh. The video record is about mesh, finer mesh, local mesh control, mesh refinement, etc. Okay, that is the project folder. And then, in Inventor, to be able to define that work is a project, well, the condition is that within inventory environment there shouldn't be an active file, and also, well, from the list of the names of the projects, the selected option will be not a certain specific project, but no project. There will be no active project. There should be no active project in inventory environment. If we select default option, then there will be no active project. So if it is okay, then can define the work as a new project. Clicked on clicked on File tab, and then move the cursor on the Manage option, then shift the cursor to this pane and clicked on Projects option. And then, yes, in the dialog box, clicked on New Project button, and then define the work as a single user project, especially if it is a schoolwork. Clicked on Next, and then write a meaningful name as the name of the project. I'm going to say mesh, about mesh, mesh control, local mesh. Okay, in short, say that mesh. I can understand that it is about mesh size, finer mesh, mesh control, etc. Clicked on this button, quite well, to show the folder of the project. I have already created the folder. It is, I'm sure, within this computer. Okay, in this partition, and then, well, it is in which folder? I have lots of folders. As I remember, I created the folder here. Yes, mesh is the name of the folder. I found it, and then say OK, indicate and OK. That is it, and then clicked on Finish button. That is the thing to do for defining the work as a project. Well, if the work has been defined as a project, then the pack and go process can be applied, will be applicable. If the object is an assembly, applying pack and go process in the end, we can gather all the files created by the user and also created by the software, collect all the files, and have them within the project folder. And also the other advantage of defining the work as a project, well, when we clicked on open an existing file button, Inventor automatically allows us to see the project folder, and without making a search, without indicating the address one more time, then automatically the project folder is selected, and its content is dropped to the screen in the dialog box. Or when we clicked on Save button, then the address is automatically selected as the project folder, via which we can save time and effort. Okay, clicked on Done tab, and then yes, deal with the rest. Okay, I remember the size of the prism to create 150 by 6. Okay, and there is a hole. Its diameter is 19. It's a true extending hole, simple hole. Okay, I know. Clicked on New File Creation button, and then select the unit system, metric, and for creating the model of a single part, that is the template to select, template option. And then create the model. Model creation starts from sketching stage. Clicked on to the sketch button, and then select one of the planes. These are defined by the axis of the coordinate system, x, y, x, z, y, z planes. Okay, I know the object is a rectangular prismatic object. Create a rectangle, and then I remember the size, dimensional constraint from here to there, it is 150. Okay, the height of the prism is 50. Finish the sketching stage and apply the extrusion process. The thickness of the slab sheet is 6 millimeters. Okay, and then start the drilling process. The drill diameter, I remember, is 19, and it is truly extending, non-standard hole. Okay, indicate the starting surface with a click arbitrarily, and then say that the location dimension for the longitudinal axis of the drill relative to this edge is equal to 75 millimeters. Okay, relative to this boundary, it is 25 millimeters. It is truly extending, and then say OK. Yes, that is the model of the object converted to solid model. Well, I do not remember the material. Have a look at the title block. At the title block, I see the material of the object is aluminum alloy 6061 is it is called. Okay, at the end, slender end, this end, right side surface or left side surface, both of the side surfaces, we have a tension type load. The magnitude of the force is 2 kilonewtons. Okay, here, and at the opposite side, opposite directed force, it balances the effect of the first system, other system. Okay, continue. Assign the material, clicked on this button, and then aluminum 6661 is this one in the list. Right click and assign. Okay, now it is the solid model of the object. I'm going to save the file. You know, order is important. Before applying the stress analysis, performing the analysis, well, the model is to be created and saved. And after the analysis, save it one more time. Okay, save as. Yes, it is the project folder. Inventor knows the address. And the name of this object, it is the model of the object. I don't know, say. Okay. It is, let's say, a piece. Structural element. I couldn't find a name. Well, I said piece is the name of the component. Okay, and then, well, stress analysis, perform the analysis. But in doing this, I know from the theory and also experimental remarks, and also, well, today, from theory of elasticity, theory of plasticity, and some CAT studyings, in the vicinity of the discontinuity, here it is a hole, where the stress will be maximum, and well, the vicinity of the discontinuity is the place where there will be stress concentrations. Okay, so, well, obey to the recommendation. In the vicinity of the discontinuity, use a smaller sized element, finer mesh, greater number of elements. But the other part, it is sufficiently away from the discontinuity. Well, use a greater mesh size. For that purpose, we have two alternative techniques. In one technique, under our controls, the control of the user control, Well, select a finer mesh size. Okay, finer mesh size. Local mesh control is the name of the facility. Okay. The other technique use refinement facility of the software, iteration technique. Well, I'm going to talk about this technique. First, why not? First, talk about this technique. Yes. Yeah, one technique we say local mesh control in the vicinity of the discontinuities, also well abrupt changings. Since there will be greater stress values, stress concentrations, well, at such places need to solve the problem more accurately. Can achieve this using finer mesh, smaller sized mesh, greater finite elements. Local mesh control. Under our control, we select the tool of the software and then yes. Select set smaller sized element for such parts. The other technique, yes, related with convergence in inventor stress analysis. Well, it can be seen that if we increase the number of elements, well, the results of the analysis changes, can most of the cases greater stress value. Okay. Of course, this does not mean that okay, increase this the number of elements, so well stress will also increase, but there is a limit, of course. If we have infinite number of elements, then the solution would be exact. Not infinite number of elements, but using more elements can find the stress value as sufficiently accurate. Well, in doing this, we start a course size, and then every successive step repetition we decrease the mesh size, and then well make a comparison. If well the result of the new say trial is greater, but the difference between the previous result and the last running is well, let's say for instance only 5%. We have a difference but 5% or 10%, depending on the accuracy of the calculation, requirement for the accuracy of the calculation, then we can select a suitable CS value, stop criteria. Well, clicking on this button, okay, in this technique, well, and having via which this such a dialog box, we say that make the refinement, I mean step by step, every repetitive runnings, decrease the mesh size. Okay, solve the problem, selecting a certain mesh size, and then make a comparison whether the value of the last analysis is greater than the previous analysis, result of the analysis, but the difference between them is, in this example, you see stop criteria is 10%. If the difference between them 10% or less than 10%, then do not repeat the calculation. Say that convergent solution converge to its final value. If the difference is greater than 10%, then continue to repeat the solutions using smaller size finite elements, smaller mesh size. Okay, yeah, well, decrease the mesh size where? At the places where the stress is maximum, and also at the places in this example, the stress at such places 75% of the maximum stress. If the stress at a point, at a place is in the order, it is 75% of the maximum stress or greater than that value, then this means such places stress is higher, so need to use say smaller sized elements, need to increase the accuracy of the solution at such parts. Well, in the dialog box, writing those numbers, we say that 5 times repeat the calculations, and for each check whether difference between the previous and the following calculation 10%. If greater than 10%, then check at which point the stress is maximum or 75% to its order of the maximum stress. Then at all of such places, decrease the mesh size for the next iteration, next step of the calculation process. Well, okay, maximum number of H refinements. That is the meaning, maximum number of H refinements. Well, 5 times repeat the calculation, but each of the running decrease the mesh size. Where? At the places over there the stress is maximum or 75% of the or greater than this value, or what, of the maximum stress. Okay, so H refinement threshold extends 0 to 1. Okay, well, here this threshold 0 to 1. If we select, of course, 0%, then this means not only in the vicinity of the abrupt changings or discontinuities, but entire of the body, each step decrease the size of the mesh size, use finer mesh, minor mesh. It sounds good, but it requires much greater calculation time and very powerful computers. Only at the places where the stress is highest or well, closer to higher value. In this example, if the stress is 75% of the maximum stress at that point, in the vicinity of that point, use smaller size mesh. Okay, I'm going to first use this technique, refinement technique, and software automatically decrease the mesh size till the calculation converged. Okay. Clicked on environment step for starting the analysis. Well, if we know that material will be in elastic region, yielding will not occur. Since it is easier to use, uh, classical stress analysis tool of Inventor is recommended. Not Nasran. Nasran is more powerful, but well, for simple analysis, it is too complex. There are lots of tricky details to know. Okay, first try to use a classical tool of Inventor, stress analysis tool of Inventor. When we run the problem, solve the problem, if you see that yield limit will be exited, then change the analysis tool, use Nasra. Okay. Click on create study button, and then in this example, well, our purpose is to determine the stress distribution. Object is not accelerated, not decelerated. It is under static conditions, so static analysis. And then, well, material, I am sure I have already assigned the material. Well, one more time, have a look at, clicked on this button. Yes, aluminum 6061 is in the row. Well, inventor knows that is the material. If you forgot assigning the material, then well, after bringing this dialog box, clicking on materials button, we will assign the material. Okay. And calculating the factor of safety or checking the factor of safety, threshold value is yield strength, while the other case may be ultimate tensile strength. If plastic deformations are allowable, okay, while the object is being used, if it is allowed to having plastic deformations, then the threshold value may be ultimate tensile strength in calculating or saying something about the safetiness. Here the measure is yield strength. We don't want to exceed the yield limit. We don't want to have plastic deformations. Okay. At this end, I'm going to fix the connect the body. So it is a constraint. Clicked on this and then indicate the surface. It has been fixedly connected to the chassis of the structure, let's say. At the other end, well, the load is 2 kilonewtons. It's a distributed load. Okay, 2000 newtons is the magnitude. Well, it is normal to surface. If it is oblique or inclined, then select this little box and write the Cartesian components of the force. But here I know it is normal to the surface, not compression but tension. Change the sense. Although inventor uses only one arrow to say that there is such a boundary condition, but it is not a point force. It is uniformly distributed force. Okay, it is to apply over this tip surface. Okay, the weight of the object is negligible, so well, no need to click on this button. No need to fix the direction of the attraction force system. Okay, if it were a very bulky object, then we would say that relative to the magnitude of this force, it is not negligible. So we would consider the effect of the gravity force. But in this example, it is negligible. Now, well, the purpose is that check whether in the vicinity of this discontinuity here and there, stress is gonna be maximum. Yes, I am sure it's gonna be maximum. And then can check whether that maximum stress might be computed multiplying the average stress with the stress concentration factor. That factor can be gathered from this table. Where it is? Yes, not table, sorry, this figure, this graph. Okay. In the vicinity of discontinuity, I'm going to allow the software to use finer mesh using refinement technique. See how. First, create the mesh, discretize the body using the default mesh size. Well, here at present, the mesh as an average mesh all the finite elements in this mesh almost in the same order of average size. There are 276 finite elements. Okay, in the default configuration of software, divided the body into 276 finite elements. Here, to be able to have finer mesh via which calculate or determine the stress value more accurately in the vicinity of this discontinuity, I'm going to allow the software to decrease the size of the mesh at each refinement stage, each iteration stage. Okay, click on for that purpose convergence setting button, and then in this dialog, if maximum number of refinements is kept 0, then there will be no refinement. But if we write a number, for instance, make the iteration let's say 6 times. If it is greater than 5, then the program notifies us, say that runtime may be too much. Not 6, but write for instance 10, 20. The running time will be drastically increased. Be aware. Stop criteria said that 10%. I'm going to decrease the stop CS criteria 5%. If the new calculated value, stress value is 5% greater than the previous one, or the difference between them 5% only, then no need to repeat the calculation, no need to make one more refinement. CS, stop. Okay, each iteration use a smaller size element at the places where the stress is 75% of the maximum stress or greater than 75%. Okay. Yes, after this setting stage, say OK. Friendly notice, the specified number of refinement is larger than 5, so may result in time-consuming study processes. Shall we continue? Yes, I'm going to continue. And then yes, run the software. Solve the problem. Click on this and then say run. Yes, calculation is just being completed, and you see, as it is expected from the previous studyings, from the reports in the literature, it is as it is expected in the vicinity of the discontinuity here and there. We have the maximum stress. Stress is maximum here and there, and since I enabled the software for decreasing the mesh size at each repetition, where in the vicinity of the discontinuities, in the vicinity of the places where the stress is maximum, or stress is greater than the 75% of the maximum stress. Now you see inventor, thanks to this allowance enabling, decrease the finite element size, decrease, and then finally using last running this order perform the stress analysis. In the vicinity of the discontinuity, you see, thanks to this allowance, the element size is smaller. We have more elements, which here the result of the calculation in the vicinity of such a discontinuity is more accurate. Okay. This is one of the techniques. The other technique, yes, under control, not making iteration, using local mesh control, can use a smaller size mesh. Okay, I'm going to save this file. Okay, finish analysis, and then click on save button. Okay. We clicked on environment step, and then start the analysis. Problem is the same, but since I'm going to use a different technique, I'm going to define the studying as a new studying. Clicking on create study button, I'm going to have one more analysis. Okay, it is again static analysis. Okay, and now you see the previous analysis now is inactive, and I have at the browser the icons, okay, for this new analysis. Quickly define the boundary conditions. Fixed connection at this end, apply, close. At the other end, the distribution load, the magnitude is 2 kilonewtons. 2 kilonewtons. It is normal to surface, not compression but tension. Flip flow. And then say OK. Well, generate mesh using default configuration, and then not refinement technique but local mesh control technique. Clicked on this button, and then, well, in the vicinity of discontinuities or say abrupt geometrical changings, use a finer mesh. Well, the average element size in the default configuration of the software, have a look at 10% of the overall size. Overall size, maximum size of this prism 150. 10% is 15 millimeters. Average finite element size is in the order of 15 millimeters. Okay, so 15, and writing the local mesh control technique, writing or selecting the mesh size. Well, I'm going to use a smaller size. Say that not 15 millimeters. Here it is not percentage. You see element size, directly right. It is size value, not a fraction. Okay, say that the finer elements, smaller size elements, these are to have in the vicinity of discontinuity. 15 is the average size, element size. Let's say 3 millimeters. Okay, and then, well, indicate the phase. Well, in the vicinity of the surface, okay, we're going to use smaller size elements. I indicated the surface, and then say OK. And then generate the mesh. Click on this button. Well, refinement factor is 0. The technique because is not refinement technique. Keep it 0. Use local mesh control. Okay, generate the mesh. 3 millimeters I said, and in the vicinity of the surface click. Yes, already assigned. Well, here, okay, close this dialog box, and then, well, at the browser, this Thunderstrike symbol says that mesh is not updated. Update mesh. Since I selected local mesh option, now Inventor notifying me that mesh is to regenerate. Update mesh. Yes, you see, in the vicinity of the indicated part, yes, Inventor used smaller size mesh. What is the order? 3 millimeters. Or say that smaller. I clicked on this one, and then not 3 millimeters, but let me say 1 millimeter. But of course, decreasing the size, then it can have more elements, and correspondingly calculation time going to be greater. And then indicate the surface. Okay, well, mesh, local mesh, open, and then, well, since I have already used local mesh facility, well, to be able to change the local mesh size, at the browser, find the corresponding icon, drop the list, clicking on the cross associated with mesh option, and then find local mesh control folder, and open that folder, and finally find local mesh option, and then say edit local mesh control, and then in doing this, not 3 but say 1, let's say, and then say OK. Now after making this changing, yes, again Thunderstrike symbol has just appeared in the vicinity of the icon. It means need to update the mesh. Bring the cursor onto this, right click and select update mesh option. You see, now in the vicinity of the discontinuity we have more elements, smaller sized elements. So, well, in this region, the stress values gonna be more accurately determined. And then run the problem. Yes. Now the stress is 24.5 megapascal, non-stress stress. Okay. Now, using local mesh control technique, I solved the problem and I found the maximum stress here and there. The stress maximum 24.5 megapascal. How about the previous analysis? Bring the cursor onto this, right click the mouse and select active option, activate. Now the previous studying is active to its results. Well, clicked on this listing arrow and then, well, as the Von-Mises stress distribution, right click activate. Well, here, using refinement technique, enabling the software to use repetitively decreasing the mesh size. I said that use this refinement technique. The maximum stress we found 24.47. Using local mesh control, we found the result as 24.5. The same, almost the same. However, in refinement method, well, after completing the analysis, to be able to check whether the calculation converge to the final value as the convergence curve. Clicked on this. Yes, I see. Well, inventor using this iteration techniques found the maximum stress first using very coarse mesh size 9 megapascal, and then well, decrease the size of the finite elements in the vicinity of the points where the stress is greater than 75% of the maximum stress. Second refinement stage, the stress value found as equal to 13.2, and then the third one near to 17 megapascal, and then the next one 24.4. And after this refinement stage, solution this is converged, and then stop criteria satisfied. I said 5% is the 5% difference is to say that yeah, the solution is sufficiently correct. Stop the repetition, stop the iteration. Yes, I see from the curve it has been satisfied. That's good. Okay, dear students, both of the techniques, which one is convenient for you, you may use. Okay, local mesh control and refinement technique. Don't forget, if well, we have within the structural element a discontinuity or abrupt cross-sectional changing, then obey to the recommendation. Use finer mesh size, smaller size mesh in the vicinity of those places. Okay, then, dear students, that is clear, I hope. Ending this video record.